Our next topic is the concept of momentum. Now, momentum refers to the amount of motion an object has. And we could see, looking at some pictures, that that's going to depend on both the mass and the velocity. Because there's a lot of motion if, say, a small object's moving quickly, or if a large object is moving more slowly. So mass and velocity both affect the amount of motion. Okay, so we define then the momentum as being the product of mass and velocity. It is a vector quantity, and the vector will just be in the same direction as the velocity. Now for the units, that's going to be kilograms times meters per second. Note that kilogram meters per second is equivalent to a Newton second by this derivation here. So an estimation exercise we'll do in class. Let's prove that momentum change is mass times velocity change. Well, change of momentum means final minus initial. I should make all of these vectors because they all have direction. Final momentum is mass times final velocity. This is mass times initial velocity. And I can factor out the mass. And then I've proven the result, because this obviously is the mass, and this is the velocity change. So the change in momentum is the mass times change in velocity. We'll use that now to prove the impulse momentum theorem. We'll start with Newton's second law, F net is ma. That tells us that an acceleration is a net force over a mass. If you use the kinematics equation and solve for acceleration, it'll be final minus initial velocity over time. Now those two expressions have to be equal to each other. Because they're both expressions for the acceleration. If I cross multiply time up on this side and mass up on that side, then I find that force times time is mass times velocity change. But of course I just proved that mass times velocity change was the change in momentum. So we have arrived at the impulse momentum theorem. And it tells us that a net force, and I dropped the subscript net on the previous page, probably, yeah, I dropped it right here. That should be F net, F net, F net. Net. There we go. So we'll put it back there. Oops, what just happened? Okay, fair enough. All right. And now, so we'll put the F net back there. So net force times time is mass times velocity change is the change in momentum. And where do we use this? Well, it turns out really to be useful any place you'd apply Newton's second law in kinematics. Here's a typical example. So we've got a baseball, and it's moving in the positive direction at 150 kilometers an hour. And then we hit it with a baseball bat. Whack. And then after we hit it, put it over here, just sort of out of the way. Here's the baseball. And it's now moving west in the opposite direction at, I guess, a final velocity, and this would be initial, of 92 kilometers per hour. And we want to find the force that acted on the ball. Now, clearly, when the ball's on the bat, the force is going to be, the impact force will be directed this way, so we expect that to be a negative force answer. And we're going to need to convert these velocities into meters per second and convert this mass into kilograms. Well, that's pretty straightforward. That first one here, that's 0.125 kilograms. And these two velocities will convert them. And then we're going to substitute into the impulse momentum theorem, which says a force times the time is a mass times the velocity change. So let's pause there and do that math. Okay, so we can now substitute into the impulse momentum theorem. The force acted for 0.075 seconds. This is kilograms. Now the final velocity is in the negative direction, so we need to be sure in this vector equation to include that. And both of these have units of meters per second. So now, for our units, it's going to be kilogram meters per second. That would be kilogram meters per second squared, which is, of course, a Newton. And so now let's see what the value is. So we multiply by 0.125 and we divide by 0.075, and it's 111.9 newtons, or 112 newtons to 3 significant digits. Now really, and we showed this in the proof, we could have solved this using Newton's second law, because with the final velocity, initial velocity, and time, we could find the acceleration, and then once you had the acceleration, you could just say force is ma. So this impulse momentum theorem is really just these two results bundled together. And so, at first glance anyway, there's no real reason to bother with this because it isn't a new idea, it's just a combination of two previous ideas. Now, I suppose there are times when it's a useful formalism, and we'll see one here in class, but the real reason to talk about momentum has to do with something we haven't talked about yet, which is the collision problem. And fundamentally, it has to do with this question right here and understanding this. So we're about to have a collision between a car and a truck. And the question is, what can we say about the collision force? Which vehicle experiences the larger force? Now, you guys have worked on this in the lab, and you should have seen, using force probes, that the forces are actually an action-reaction equal and opposite pair. So it turns out that both of the forces are the same. Now that follows, I suppose, from Newton's third law of action-reaction, but in terms of why they're the same, we should realize that they're both sort of elastic contact forces. So the car pushes on the truck a little bit, and that causes the truck to bend, say, probably at the bumper where the contact point is. Now, the bending of the bumper, of course, creates the reaction force with which the truck pushes on the car. And so the truck and car are both bending, and so those two bending forces have to be balanced with each other because one is creating the other, which is in turn creating the initial one. So they are an action-reaction pair, and they are elastic contact forces. One cannot be larger than the other. Now, that just tells us that the force on the truck is equal and opposite to the force on the car, and I suppose we could just call it F. And the fact that the forces are equal doesn't explain why the car tends to be more damaged. What that has to do with is that the car tends to be made of has a less strong frame than the truck does. So even if the forces are the same, the car is probably more likely to be damaged. In terms of the driver inside, yes, the collision forces are equal and opposite, but the mass of the truck is much larger. So with that really big mass, there's a fairly small acceleration for the truck. With the relatively small mass of the car, there's a much larger acceleration for the car. And therefore, the two accelerations aren't equal. The car has a much greater acceleration, a much greater change, and that leads to a greater change in velocity for the driver, which is more likely to cause them injury. So what does this have to do with momentum then? So we know that for collisions in a closed system, one that's cut off from the outside world, the two contact forces are governed by Newton's third law, so they're equal and opposite. Well, if we then take that Newton's third law and we multiply by the collision time, then force times time must be equal and opposite. But of course, force times time is the impulse. It's the change in momentum. So because the forces are equal and opposite, the momentum changes are equal and opposite. But what does that mean? For instance, in this collision, if the car was to lose 20 units of momentum, this side was a loss of 20, it must be that the momentum change of the truck is opposite of that, i.e., the truck would gain 20 units of momentum. So whatever the car would lose, the truck would gain. That means that momentum is transferred between the two objects and not gained or lost. That means it's a conserved quantity. Let's make that a little bigger so you can see it. There we go. So, and we could just highlight this. Here, let me use the highlighter. It's probably better. Highlighter in yellow. Okay, there we go. Since momentum change is equal and opposite, then momentum is not gained or lost. It's just transferred from one object to the other. And that means that just like the energy of the universe, momentum is conserved too. So momentum is another conserved quantity. So let's look at a typical example then. Let's switch back to the normal pen, please. There we go. So a typical example would be, say, this one right here. Oh, first of all, mathematically, how do we write the law of conservation of momentum? Well, what was the idea? If it's conserved, that means it's the same at the beginning and at the end. Total momentum equals total momentum. Now, if you have more than one object, then you'd have to add those two momentum vectors at the beginning and say it's equal to the two momentum vectors sum at the end. This is the same principle written using the fancy summation notation. And this is the way that we'll work with it because, of course, momentum is mass times velocity. So this is the total initial momentum, and this is the total final momentum. That's abstract. Let's apply it to a simple example. So here we have a block, and we fire a bullet into it, a projectile into it, and it sticks in the block, and then they move together. And this happens on a frictionless surface. Now, because it's on a frictionless surface, the only forces acting here are going to be the bullet pushing on the block and the block pushing back on it. They're an action-reaction pair. So, the forces are equal and opposite, the impulses are equal and opposite, and momentum is transferred, not gained or lost, or, another way to put it, is that it's a conserved quantity. So, you're going to have m1 v1 for the bullet plus m2 v2 for the block initial before the collision is going to be m1 v1 plus m2 v2 after the collision. But of course the block's at rest before the collision, so that's just 0. And so this is going to be the mass of the bullet and its initial speed. And then after, they're both moving together. And as a result, the two speeds are the same at the end, so we can factor it out. And we can find this unknown final speed. So the bullet was 30 grams, initially moving at 250 meters per second. So we'll use kilograms and meters per second. So that's an expression for the total initial momentum. Now the total final momentum is we've got the bullet plus a 5 kilogram block. So we essentially have a 5.03 kilogram block, moving it at a known speed v, and we can now solve for that unknown speed using this momentum equation. So divide by 5.03, and we find 1.49 meters per second for that speed. Now, although the momentum was conserved in this example, the mechanical energy is not, because in this collision, So we start off with kinetic energy of the bullet, and then we end up with the kinetic energy of the combo. And then collisions generate significant amounts of heat, as we're going to see through this calculation. So there's no potential energy here. There is just kinetic energy. So here's the bullet. There's its initial kinetic energy. And then here's the 5.03 kilogram combo object at the end, now moving, we know, at 1.49 meters per second. Now this answer is quite striking, because if we do a half of 0.03 times 250 squared, come on, we see that there was originally 937 joules of kinetic energy. But then how much is there after the collision? Well, the mass got big, but of course the velocity got very small. So there's now only 5.6 joules, 5.58 or 5.6 joules of kinetic energy left. So we lost virtually all of our kinetic energy. Most of it got transformed into heat. So we lost 932 joules of it. And the fact that it's a loss is just reflected in that minus sign. So that was lost to heat, or it was lost to the work that was done by the bullet pushing into the wood material. Now, there's some words that we'll need. This was a completely inelastic collision where the masses stuck together. Although momentum's conserved, assuming it's frictionless in a closed system, the kinetic energy was not. Mechanical energy was not conserved. A lot of kinetic energy gets transformed into heat. There are idealized collisions called elastic, where the masses bounce off each other and there's no heat energy, and in that case, kinetic energy is conserved. Really, this is an idealization that never really happens in any real collisions. What happens in real collisions is the best you can get is what's partly elastic, where they bounce off each other, and there's some loss of kinetic energy to heat, but not very much. So say, billiard balls colliding off each other. There's not a lot of heating there, and those collisions are fairly elastic. Now, the reason we call them elastic, partly elastic, is that when the masses hit each other, say this is them flying towards each other, they actually deform elastically, like this. And as a result, as the material sort of has to change shape and molecules have to push through each other, there's inevitably a little bit of heating. But in the idealist case, what would have to happen is these objects would have to deform, and then they'd have to bounce back to their original shape, and there would have to be no heating associated with that. Those molecules would have to slide past each other with no no internal friction occurring. Okay, so this collision problem then is a new and interesting and useful one, and that is really the main use of the momentum concept. So when we meet together, we'll look at a couple of demonstrations and fill in some of the things we've missed, and then we'll practice working on collision problems. So that's our pre-lecture video for today.